Hi guys, in this video I cover Big O notation. Big O notation is used to measure and compare the performance of algorithms. Now before we dive into Big O notation, let's first clarify what an algorithm is. An algorithm is a finite sequence of steps that provide a solution to a problem. It is not specific to any programming language and is often expressed in pseudocode. Now, when we have multiple algorithms, we want to be able to compare them. And what do we compare? We focus on speed and on space. Speed is the runtime. How long does it take for an algorithm to produce results? And the space is the memory requirements. How much memory does an algorithm need to produce results? Sometimes we also focus on clarity to see how maintainable an algorithm is to adapt to future changes. Now, why do we compare? Today we have computers that are so powerful that it doesn't really matter if an algorithm is fast or slow, right? So that is actually incorrect. In particular, we will learn that as the input size to an algorithm grows, we want to see how that impacts performance. So we want to know time complexity, space complexity, but in particular, scalability. Like I said, when we increase the input size, how does that impact time and space? For example, if you have an algorithm that is based on an array of 10 values, how fast is it and how much memory does it need? And now if I give that same algorithm an array of 1,000 values, how fast is it? How much space does it need? And then if I increase it to 1,000,000 values, how much time does it need? And how much space does it need? So we really focus on the input size. How does time and space behave as we increase the input size? Now, typically we look at classes of functions. So we look at constant, logarithmic, linear, linear times logarithmic, quadratic, and exponential. You may have noticed the x's that I put in front of quadratic and exponential, because these are really considered infeasible. If we have an algorithm that takes quadratic time, as we increase the input size, it just becomes way too slow. Say if we have an algorithm that operates on an array of 10 values, it would be 10 times 10, so 100. Now, if we give it that same algorithm an array of 1,000,000 values, it would be 1,000,000 times 1,000,000. So it becomes way too slow. So we really want to design algorithms that are below quadratic performance. Now, how can we analyze algorithms to see on what class an algorithm belongs to in terms of performance? We could execute it on a computer, but that really just measures a computer to another computer. It doesn't focus so much on the algorithm itself. So it's not a good method of comparison. We could also count the number of statements, but that focuses more on the programming language or the programming style, and a few more statements or a few more statements less doesn't really have big of an impact. What we want to focus on is loops. Loops that depend on input size. So again, if I have an array, I want to check and focus on the loops that operate on the array, because I know when I give a larger array, there is more iteration performed on the loop. And also we want to focus on recursion. Now in this video, I only focus on loops, so you get a basic understanding of how it works. Then we want to focus on the worst case scenario. It doesn't help if the algorithm is very fast, but that happens only 1% of the time. So we really want to know what is the worst case scenario? What is the guaranteed time that it executes? So in order to describe the performance, we use Big O notation. Big O is used to always describe the worst case performance of an algorithm. It is also used to describe the worst case space complexity of an algorithm. Once we have the two, time complexity and space complexity, we can use these to compare algorithms. And important is that Big O is always based on the size of the input. and the input is referred to as n. Now, where does the big O come from in big O? It comes from the order of magnitude. And big O is written with a capital O followed by parentheses with then the class of functions. And X, like I said, describes the class of functions. It is always determined by the most dominant term for a function. So let's take a closer look. For example, O1 would be constant time. O log n would be logarithmic time. On linear time and On square quadratic time. The same refers to space complexity. So O1 would be a space complexity of constant. Now let's take a look at running times. If we have n, it would be On. If we have n square, it would be On square. If we have 2 to the power of n, it would be O with 2 to the power of n. So n again is the input size. If we have an array, the size of the array would be n. And if we loop over the entire array, we would get n, 1n. We iterate over it one time. Now what if we have 10 times? So again, think of an array. We iterate over it 10 times, we would get 10n. This is still in the class of On. If we have 4n square plus 2n, this would be quadratic time, On square. If we have 7n cube plus 3n square, this would be On cube. So we always focus on the most dominant term. The reason for this is, as we scale up the input size, and the larger the input size get, the lower terms really have much less of an impact. So they matter less and less. So what do we look for? I mentioned we look at loops, but not any loops. We really focus on the loops that depend on input size. Now, if we have a single loop that depends on input, we have On. Then we also look at nested loops. So we have an outer loop and an inner loop. We have a nested loop. If they both depend on the input size, we have n quadratic. Now let's go over a few examples so that you see how this works. Here I have a function, sum up, that gets a vector of integers as input, and it uses a loop to iterate over all the elements of that vector. And it sums up the elements and returns the sum. So what is the time complexity and what is the space complexity? For time complexity, I mentioned we look at loops. And there's a single for loop, starts at 0, iterates over all the indices of the array and sums them up. So this for loop depends on the array. So we have On. On, because the array is the input and the array size is n. So we do this n times. So we get On. Now the space complexity is O1. For space complexity, we look at what additional space is needed for the algorithm. We do not count the space of the input. So the array size doesn't matter. We really look what does the algorithm need to compute the results. It has a single variable here. So this would be constant 1. It doesn't matter if I give an array of 10 values or 1,000 values. There's always just a single variable allocated. So the space complexity is constant. Now let's look at another example. So this finds the maximum value in an ordered array. If the array is 0, it returns -1. Otherwise, it just accesses the last element. Now, since this is an array, we can compute the offset. We don't have to iterate over it. We just compute the offset, go to the last element, return it. So in this case, it doesn't matter if the array has 10 elements or 1,000 elements or 1,000,000 elements. We always just go to the last element directly and return it. So time complexity is O1, space complexity is O1 as well. Now another example. Here we have a single loop that goes from 0 to 10 and sums up the values. Now the input array is not used in the loop. So the loop is constant. because it doesn't matter if the array has 10 values or 1,000. We perform this loop, or we iterate over 10 times, 10 iterations. And space complexity is also O1. There's just a single variable. It does not matter how large the array is. Now another example, 2 nested loops. The outer loop, we can see, depends on the array size, and the nested loop goes from 0 to 10. So this would be, if we consider the array size n, the outer loop would be n times 10. So for each iteration, it does 10 iterations of the nested loops. So we get 10n. And 10n is the class of On. So the time complexity here is still On. The space complexity is O1, is constant, because we just, again, need a single variable. Now another example. 2 nested loops, both just go from 0 to 10, so they do not depend on the input. And so we have 10 times 10, if you will, but it is constant. It's always the same number of iterations, no matter how large the input is. So we have O1, and space complexity is O1 as well. Now another example, 2 nested loops again, but in this case, both loops depend on the array size. So both depend on the input. So whenever we have nested loops, we can multiply n times n, and n times n gives us n squared. So the time complexity here is quadratic, O(n) squared. The space complexity is still constant, O1. Now another example, 2 loops, but in this case they are consecutive. We have first a loop that depends on array.size, followed by another loop that depends on array.size. So both of them depend on the input. And when we have consecutive loops, we add them up. So it's n plus n, or in other words, 2n. Now 2n is still in the class of On. So this is still linear. It doesn't matter if it's 2n, 4n, 10n, it's still in the class of On. So consecutive loops are much, much better than nested loops. Remember that when we have nested loops, we multiply n times n. If we had another nested loop here that depends on input size, it would be n times n times n. So n cubed. Versus when they're consecutive, we just add them up. N plus n plus n. So it's much better to have 3n, which is in the class of On and linear, than to have n cubed, which is in the class of n cubed. Now, one more example. I have an input array. In this case, I allocate memory for a new vector inside the function as a local variable. And then I iterate over the input in reverse order and push the values into this reverse vector, which I then return. So it's a single loop. The loop depends on the input. So it's On. And the performance in terms of time complexity is On. So it's linear. Now space complexity, we can see we allocate a vector, and the size of the vector directly depends on the input. So if we pass an array of 10 values, we push 10 values into this local variable. If the array is 1,000, we push 1,000 values into this local variable. So in this case, the space complexity is On. It's linear. It depends linear on the input. Now, what have we learned? To recap, we use big O to measure the worst case performance in terms of time complexity and space complexity of algorithms. And then we can use the performance to compare different algorithms. When we measure this, we always focus on loops that depend on the input size. Note that it's important that when you have loops that indirectly depend on input size, that you do count them as well. Once we know the loops, we can come up with the class of functions that an algorithm belongs to, like we just did in the examples: constant, linear, logarithmic, and so on. I hope you enjoyed this video. Thank you for watching.